be covering the I/O input output of Haskell. So everything from like basic file writing to requests, as well as like how does I/O actually work in Haskell and what makes I/O different than other
Yeah.
languages.
Thank you for the introduction.
No worries.
So yeah, so I/O stands for input output, obviously, um, but it's kind of one of the most important pieces of programming because you want, at the end of the day, your program has to do stuff. Um, I mean, you can't have, like, if you were to just have a completely pure application, it would basically run, and then you would not know that it ran because it wouldn't tell you that it ran. Um, so the output of a function, um, if I can, just for a minute here, actually.
I guess a good
So
example of that would be like if you just did addition, but you never printed out the
yeah,
result of addition, right?
yeah. Give me a second here. Um, I'm not sure if people are familiar with std in and std out, but I will just give a quick overview and where you can kind of find more information about this. So basically, every computer has these buffers or streams on the computer. Can I find it? So there's typically three. Someone's got a lot of background noise right now.
It's Galen.
Sorry, I'm
Cannon.
trying to fix my. Is this okay?
It
Yeah,
is now, yeah.
I
it's
think.
better.
Sorry, I noticed on some of the past videos that like my voice would be very quiet, and
True.
so I'll just what I'll turn up the audio a little bit, but I'll just mute myself.
Sounds good.
Yeah.
Okay, so all of this really comes down to, like, these buffers are from C, and C actually communicates with the operating system to be able to do these. But there's three typical um, sort of like pointers that you can reference. One's standard output, one's standard error, and then where is it? Standard input should be here as well. Right, it was past it. Standard input. So basically, these are just like standard streams that your computer will read information from. Um, and so, like, anytime that you're viewing information, you're probably viewing it through standard output. If you're sending information into your program, it's going through a standard input. Um, and then even using a socket eventually will come down to standard input to send it into your program. So I just wanted to give a quick kind of background on that, just so you know what's actually happening. So the first example I'm going to do is just like the hello world of programming in Haskell, and it's just hello Haskell. So we're going to, if you take a look here at the type signature, everything that has anything to do with IO, or anything that has side effects in our program will always have this IO type. So you can think of IO as like the primitive value of side effects in Haskell. This is great because it's impossible to do anything, because we know that Haskell is a immutable language, so every function that you write must be pure. But this is the, I guess, one exception to that rule. And it still is technically pure because it's defined behind a type. But this type represents the idea that we're leaving our program runtime in order to make something happen. So in this case, we're saying IO, meaning a side, like anytime that you see IO, I'm just going to put a little note here. It's basically just saying that there's a side effect to our application. And so what we're saying here is that we've got IO, and this is the unit type. So if you haven't seen this before, this is kind of like void in other languages, but it's represented as a type. So it's basically just the absence of a value, meaning we're going to do IO, and then we're not going to return any value, and you'll see why in a second. So we're not actually returning anything from this function. What we're doing is using the put stir line function, and I'll get and show this in a second, to this function here prints to the standard output. So there's also print, but this is basically just print with a new line at the end of it. And so if we go over to Google, just take a quick look at put stir line. This is part of the base prelude package. And you can see that it is oh, I clicked on prelude, not on, there we go. Oh, wait, what? Let me search for it.
Sometimes it just takes a second.
Yeah, it's a big file, so. And my computer is anything but fast.
It might be a good time to say, what do you mean by side effects? I'm not sure if that's like a globally understood concept.
Right. So how do I explain that? So okay, so a side effect is something that we don't control. Like we don't control the response. So for example, let's say we make okay, let's say we have some weather API, right? And we're gonna send our request, or we're gonna send a request from our application. Okay, we want the application to tell us what the current temperature is, right? So we can say, our app sends a request over to a weather API, and it's going to, there might be three possible things that it can give us, right? It might be, and I'm not sure how I'll model options here, but basically it could give us either a valid response back, or it could give us a like some kind of authentication error, or maybe the server is down, like maybe because this weather API is handled by someone else. We don't control what actually occurs inside of the server. We're just sending a request. Basically, as far as we're aware, we're just sending a request and then waiting for a response, right? And so the idea that we don't have, like, basically it's the concept that we're leaving this application runtime. So within our application, we can write a bunch of pure functions. Right, we can say right, we can have some like logic in a pure function. This is inside of our program's runtime. This here is saying, but this on its own, like we can't use this without IO, because if we called this function, we would have no idea that it even ran, because we need to leave the program runtime to go to our like to print it to the screen. So like those 3 buffers that I showed you, standard input, standard output, standard error, those are running outside of our application runtime. So they're side effects like
So I guess like the side effect would be that like your program deposits something in standard error. Like
yes,
right, because standard error is not a part of your program, but your program has, like a non side effect would be the program affected itself. The program affected its
yeah,
own internal state, whereas the side effect would be that it affected something outside of the program runtime, like a buffer, or another computer, or a buffer
yeah,
on another computer.
yeah. These are all examples of side effects that you can do, and it's the idea that it's like we're doing something that's outside of the application. So anytime we're like talking to the computer, that would be IO. Like the list could go on, right? But these are examples of what IO would be. Can you think of any others?
No, but I do want to add that, like, ultimately, like, I'm sure you guys know, like, these are the same as any other language, right?
Yeah,
Any other language, right? Haskell's nothing special in this regard. Any language can write to a file, read a file, do a network request, get the current time. The only key difference is the Haskell type system.
yeah,
And so, like, for example, if, like, let's say, like, run hello Haskell was of the type IO string, I as a programmer, as a reader coming into this Haskell program the Kyle's written, I can see that an IO string is not created equal to a string. Um,
yeah. I have examples of that later on in the
yeah, and we'll
thing,
get to
but
that. Yeah.
yeah, let's start with just IO pure or IO unit. But that's exactly it. So the big difference, and so, okay, so why do side effects matter, right? Why do they matter? They're what the user sees and what the user interacts with. And so the like the number one source for error in your code are these side effects that occur, right? So because we don't like, we've talked about the concept of purity where it's like every like this function will always give me the same value. Like if I put in test here, this function that like there's never a case where this function will give me anything. Like there's never a case where this will give me anything other than test hello, right? Never. Like it's impossible for this to give me anything other than this. But for something like this one here, it is now, this is very unlikely because this is just using standard output, and if standard output was breaking, like we would not be able to even run the application. But in theory, run hello Haskell could give us hello Haskell or some error, right? And this error here would be defined by the operating system. Like maybe you've like somehow deleted your standard output registry. Um, that I don't never seen that, but
Broken pipe even, or
yeah, like a pipe got disconnected. You maybe because you can divert your pipes to different file locations. So maybe you diverted your pipe to a file location that you don't have access to. So this is like giving you like a permission error or something. Um, but you can think about it as like if you've ever seen an exception in your code. Well, actually, I can't even say that because other languages they don't enforce purity. But in Haskell, if you see an exception, it's because it's done some form of IO. Um, And so I'll get more into some of these like some of these other examples I think will show this better. But just understand that like this is a pure function. It'll always give us the same value every time. This is an impure function. It's a very simple impure function. But the idea is just to, if you understand one thing, understand the difference between a pure function and an impure function.
And
And I'll show more examples of that in a minute here.
and I want to like expand on that, like, you because you might be thinking like, well, my pure function, that's like a very simple function, but this even holds true as the types get more and more complex. Like we could have, you know like a deeply stacked, that I won't say any specific examples to not confuse, but like if it was a way more complex type and there was a lot more going on, even more arguments to the function, it would still be that the same combination of arguments gives the same output every single time, right? So if you had a
Yes.
function that took four integers and we gave it 1, 2, 3, 4, and that gave us back 10, then it will always give us back 10. Um,
Yes.
you know,
But if we had, if we have some function that like multiplies by the time of day, then every time we call that function, it's going to give us a different value,
right.
right?
And even further, like just reasoning from the types there, like let's say the same exact example of like we're gonna give some function 1, 2, 3, 4, but this time instead of it returning an int, we see that it returns an IO int. What that means to us is that there's probably some IO action that's happening in the middle. So that could be that it reads from like an unknown file, like unbeknownst to us, the user of the function, and then adds that into the equation as well, um,
Hmm.
based on some random multiplication. Right, so 1, 2, 3, 4 in the first example always gives 10, whereas in the second example the function could be designed that one time it returns 11, the next time it returns 22. And it's important that we have the ability to deal with this chaos. Because if we didn't have IO and side effects and the ability to read, from the outside real world, like we couldn't take a network request. How would we ever interact with users, right? And since we're interacting with users, you know, even in the context of something that is pure, right? Well, sorry, even in the context of something that's written well, the user can give um, anything that's allowed by the API, right? So if we say that this API takes any integer, we have to be prepared to take any integer. And so IO ultimately, this distinguishing between IO type, IO of integer and just an integer is very different and helps us to write our programs better so that we can deal with the chaos as it comes up.
Yeah.
And what we'll see is that, like, you know um, we're combining pure logic with impure APIs ultimately. So
Yep. Yeah, and I've got examples of all this. I actually think it's going to become more clear with this next one here. So we are going to write a function that gets someone's name and then says hello to them, right? So this function, quite literally, every time you run it, will have a different value. I don't know what the heck's going on there. Okay, whatever. Oh yeah, fixed it. My formatting's weird today. Okay. So this is a very simple function. I don't know why this is dark, but whatever. Did I make a typo? No.
that is
Okay,
strange.
whatever. So, okay, this function this function here, get line, if we take a look at that, is it in here? Yeah. So right here, you can see here, read a line from the standard input device. So we just talked about std in, and that's all this function here is doing. This is an input function, and you can see here it's of type IO string. So this means it's going to perform some IO action, and then it's going to return us a string. And this is a monad. We've discussed this a little bit, but the way you can read this, as you remember, this is a type signature. This is an IO action wrapping a string. So everything to the right of it is like the context within the IO action. So it just means that when we peel off the IO, like when we handle IO, we're going to be left with a string. And I think we talked a little bit about type kinds last week. That concept will take a little bit of time to marinate, but this is of the kind star star. Whereas once we deal with IO, we're left with just the star, which is the string over here. And so,
Oh, sorry.
sir, go ahead.
I was gonna even say I'm now just thinking of this in this lesson specifically, but like you could almost think of like IO and similar things you'll see in that spot, almost as like a almost like a modifier or like an access modifier. Like you'll see other things like for example maybe you can see maybe unit. And they're like access modifier. It's still the same underlying type, but it's like wrapped
You've seen
with
this
some,
one.
yeah, it's wrapped with some more information. So, like for example, in either string int, that's a way to model that you might have an int or you might have failed in getting such an int. And so it's just like an access modifier, in that the result might not actually exist. And so if that it does not exist, then we'll tell you that.
Yep. So that's I mean that's monads in a nutshell. There's a lot you can do with them, but like we haven't formally done a lesson on that yet, so
Mm-hmm.
we'll just kind of introduce that concept slowly. So this function is very simple. Uh, this here, so we're using do syntax, and this is basically just syntax sugar. So if you notice, this function doesn't have a do. Um, this is really just syntax sugar for the um, bind for this, right? Um, it's a little bit more than just like a replacement for this. There's actually like at the type system level, you get this nice little arrow. And what this is saying is that we're going to actually execute. So what's a good way of showing this? So get line has to have the same context. Like it has to be an IO action. I can't just like, do you know something that's like a reader that I can put in here and it'll throw an error?
Well, can I just go back to do syntax for a second there?
Sure. Yeah.
Yeah. So like, I think the easiest way to think about it when you're just starting out, like Kyle was talking about, we will get into monads at a later date. If you are more advanced in Haskell watching this, like, um, bear with us here, but like ultimately, if you see that you're working with IO, you can use do syntax. And so do syntax, in a nutshell, allows us to run we can do two things. We can run like a bunch of yeah. Kyle's writing out the more what is this like desugar into, and do just helps us to like write the code. Sorry, Kyle. And then ultimately, so like put string line, I know from looking at this that put string line is of the type IO something. Um, so that's that I know that that is an IO unit, so that makes sense. And so I could, for example, have like the next 30 lines being put string line of, and it will work as a type, because it will just run from the next um, first statement to the next statement. The second piece that matters is the name. So on line 33, now line 34, um, on the on the left side of the arrow is on the left side of the arrow is of the type string, and on the
Right.
can you just annotate that too, if you don't mind? Um,
What do you mean annotate?
like
Like this?
yes, and then on the right side is of the type IO string. I don't know if you have rank
Oh yeah, you
index.
gotta have.
So ultimately, I kind of will just get rid of that in a second, I guess. But like, um, if we had some extension to allow us to annotate types like that, then we would see that the types are exactly that. So the key
Mhm.
point is, okay, we have an IO string, great. How do I use it, right? Because like, for example, let's say you want to use name as an argument to my pure function. We see that my pure function takes a string, not an IO string. So it will reject a type of the IO string. So
Yeah.
ultimately, it's like I was saying with an access modifier. We need to use that bind arrow or that unbind arrow in order to get that value and then use it. Um, yeah.
Yes. So say I wanted to. That's a great point. If I wanted to call my pure function, let me just put a little prime there. So if I wanted to call my pure function with, and say I don't know how monads work. So I'm like, okay, well I want to get line on. Uh, yeah, I want to. What's going on here? Well, there you go. Actually, it's already throwing an error. So I can't even just use my pure function here. I need to go like let result equals my pure function get line. And so you can see here that get line, I'm gonna actually just, so it's easier to see the error in here, could not match the type IO string with character array. So it's expecting string, but it's getting an IO string. So my pure, this is exactly what Galen just said. My pure string takes a string, but we're giving it an IO string. But if we were to say equals my pure function name, then this is just, oh, I got rid of the E. Then this is just fine. Result 2 works, right? And so this is the idea that like we're actually like with this operation, we are handling the IO and we are unwrapping the result. And then we can use that in here because name is just a string, right? So it loads. So to demonstrate how this function works, I will run print my name, and I'm like 99% sure that it worked. Yeah. So right, and so this is the same thing here. J Kyle. Oh, it's printing the comma as. Oh no, sorry. This is. I don't know why that's happening. Anyways, we'll do it with run print my name. Have you seen that before, Galen?
I
Wasn't
haven't.
this wasn't
It's
happening yesterday?
more likely to do with Emacs than.
Yeah.
But
Weird.
I'll also add too. So like from okay. Well, the piece that Kyle just alluded there.
I'll bring
If
it
you
back.
don't understand that, that's completely fine for now. You will understand it. I think it's a good example of like the origins of Haskell is like very math focused, like a deeply based in category theory, in lambda calculus. And again, if you don't know what those are, like that's part of why we're here. We want to teach you a language like Haskell for these reasons, that this is so mathematically bound that's going to help your logic. Um, but ultimately, if you don't understand what that means for now, that's totally fine because we have this like do syntax to sort of desugar, um, or sorry, to make it easier for us to write IO statements. So, but yeah, ultimately, like this is why we are using Haskell, right? Like we're using Haskell to teach you guys to be better code, and it might not be obvious right now why run print my name is defined so well in terms of Haskell, but that's just a sneak peek at like what we will be getting into. Um,
Yeah. Yeah, and so the reason I wrote this out like this is just to kind of show you that like these two functions are identical. And so you will learn what this operator is, what this operator is, but like this is all you need to like people don't really do this anymore unless it's like you're writing something in line and you want to use like a bind just like very quickly. But for the most part, people usually use do syntax because
it's
you
just
can see
easier.
like this is yeah, this is like the actual way to define it as an expression. And the do syntax, like it will just compile it down to this. Um, but this is just like easier for us to read as programmers,
Mhm.
right? And so you can see how Haskell, it started out as a research focused language, and now a lot more people are starting to use it. And so there's a lot of these kind of tricks that are being, or these extensions that are being built onto the language that make it easier to write.
Yeah, and
Um,
and I know Kyle. Just fair warning. I know I'm talking about monads here, but like I think this is the full extent to which we should talk about monads in this context.
yeah,
Is like the reason for monad, like logic or the theory of monads, which also like there's a great concept that you already know monads. You've probably used them. You've used them if you've done like a try catch sort of statement. Um, but ultimately, like monads is the like the math behind the ability for a pure program to interact with an impure world, right? So
yeah, the world is impure. That's a good way of saying it. Like everything in the real world is going to be a
chaos.
side effect to your application, and it's chaos, right? Like we write programs to organize the real world, and in order to do that, we need to deal with the side effects, which are
Mhm.
like the actual real world that we're interacting with. And
Yeah.
so we want to limit the amount of interactions that we have with the outside world, and we want to make sure that we've properly handled every edge case.
Right.
If you know anything about like unit testing or any of these kinds of um, techniques, they're done because a lot of other programming languages don't enforce this through a type. So, like for example, in Python, there is no IO type. Like in Python, yeah, there's just no representation of like a side effect happening. So like you might have, I'll just write some pseudocode in Python for now. Like you might have like a function, uh, my, I'll just call it my function, right? And inside of this function, because state is mutable too, that's another aspect that makes this even harder. Um, you might have like, you might do some math. So you might have like res equals 1 plus 4, and then you might take that result and you might uh, you know uh,
Use input
y- y-
function.
yeah, or like let's say like I don't know the name of the function, but you could go to like my database call with res, and you could be like other, or you just say like value equals my database call res, and then you know, you might have like some if statement here that's like if value is not null, and then you might do something with the value. You might say value, or let's say like print value, else print couldn't find the error or the value in database, right? And so this is a very simple example, but you can see here like nowhere, like if I'm just reading, like let's say all of this is hidden from me, like I don't see any of that. Like I'm using this function. I'm not uh, I'm not just going in and reading, because you shouldn't have to read every line of a file or every line of a function for you to know what it does. So
Or
just looking at this type signature, you have no idea that it's actually interacting with a database, that it's printing to the line. And this really matters, especially printing inside of a function, because if you're printing inside of a function, that takes up time. So if like printing to the screen is one of the slowest operations you can do in a computer. And so if you're printing inside of a function and you don't even know, and then you use this function, you're trying to like call my function, you know, this is just pseudocode, but you're trying to like loop 100,000 times. And then inside of that loop, you're trying to call my function. Like this is going to be extremely slow. Whereas if you knew that there was IO inside of it, you know, you could kind of restructure that function. As well as this is a very simple example. There's like 6 lines of code here, but most functions that you work with are going to be a lot longer than that. They're going to like, and maybe you like maybe you follow one of those arbitrary rules where it's like if your function's longer than 10 lines, make it into another function, which I think is complete BS, first of all. But that's kind of just a side effect of like, because because you're doing too much and you don't understand what it's doing, you want to break it up into functions. But doing that just complicates things even more. Um, you know, my database call, there could be another 300 lines of code after this, right? And we don't have any guarantee that there's not something in those lines of code that will break, right? And so calling this function, like maybe my database call, it needs an integer here, or let's say it needs a float. So this is like 1.0 plus 4.0. Let's say that this is valid, but when it tries to use an integer, it breaks because it needs to, or it might not break, but it gives us the wrong value because it's doing integer division and it's just chopping off the, like integer division versus double division would be completely different result. And so like we don't have any guarantee that the function is going to work as expected. And because we don't know, because we don't even know that it's using IO, and we have no constraints on this IO, like we're not saying it must give me back an integer for example, then basically an error can occur anywhere in the program's execution. And it can occur later, like if someone else comes in and
well,
changes this function, right?
even like I'm wondering too, like with all that said, like what if you like returned the value and then try to do something with it? All those things are still true. You know, you could have like I mean, I'm
Mhm.
thinking even like not a number in JavaScript. You know, where like if you do like there was one input I used to, like I worked with on a previous project where like the if the number was like of a very particular value, it would fail and just give you not a number, and then the rest of
Yeah,
your
like
program would break.
this right here would fail if you gave it a string. but there's nothing like there's nothing stopping you from writing this code, right? And so with this function, like basically with functional programming and with pure functions, we are ensuring that everything, first of all, everything is typed. Anytime that we interact with a database, we're enforcing that it's done through this IO type. And you'll see that there's like functions built specifically for IO to handle these things gracefully. But at the very least, even just knowing that this function does some IO operation is extremely powerful, because what we want to do when we write programs is we want to isolate, basically we want to isolate any IO action to the boundary of the application. What does that mean? So say I have my main function, this is where everything starts, right? I want all of my IO actions to effectively happen in here. So I like, how do I show this without like writing a complex
You
application?
could
Like,
just do like get line like 4 times and then like add the
yeah,
result
like,
or
we're just gonna keep getting a line. Right, and so like what we want to do with our applications, and I'll just do that for now. Like we want all of our side effects to happen here. Once we call a pure function, so I'm going to now call my pure function with res1 plus res2 plus res3 plus res4.
Also,
Like,
can I make a point here? I want to like this is an accidental great point I think that we can make here. Is yes, we're like just using something simple like get line, but like conceptually, um, sorry, can you go back for a second?
mhm,
Conceptually, this is the exact same like this program, and what we're focusing on with this program does not care whether that's get line or whether that's perform network requests, or anything else, or read from database, any sort of like external activity. It doesn't care. Just ultimately, it doesn't care as long as the function is going to continue to return, some string value. Um, so yeah.
yeah. So basically, okay, yeah, this is a good way to explain it. So in other languages, there's no enforcement that when we call my pure function, each action in the do block. Yes, so anytime that we're doing this here, this needs to be an IO mode. It see here could not match type IO with maybe, and that's because I didn't constrain this. But if I go like that, it'll give me an error on the just. Yeah. So let me reload this. So you can see here, these are both monads, but you can see that we're expecting, like we can't just do any operation inside of here. We're restricted to using IO operations, which is great because this means we can't do anything that we're not expecting. Um, in say Python, like there's nothing stopping you from writing a function and then just like doing like 17 different things inside of that function. There's nothing that stops you from doing that. Here we're constraining, like we're specifying that this function will only do IO. Now we could have some kind of like transformer that says, okay, IO or maybe is okay. We're not going to get into that right now. But the key there is that everything's specified at the type signature level, and then everything's inside of the function is constrained. So you can't just add a maybe inside of here. And so yes, to answer your question, Eric, everything here must be an IO action. We can use let syntax to define a pure value, but anytime we're actually doing something in this function, like this is just defining the value of result, it's not actually using it. Once we actually put it into put stir line, then it's taking that pure value as a string for put stir line, and that works, right? So if I call main and I give it hi, how are you? It'll say hi, how are you? Hello, right? And if I, one second here, I'm gonna use my terminal just because my Emacs is acting up. So I feel like it's a little confusing seeing the J thing there, especially if you're not expecting that. So give me a second. Just split my screen like this. Go. I'm gonna go ghcio load main.hs, and then hi.
Great question, by the way.
There you go. Yeah, good question. Because that's kind of the whole point behind monads, and we'll get into that a bit more. But as you can see here, this is doing the actual what do you call it? The IO that we're talking about. And so I'm gonna get into. I'm gonna just put this down at the bottom of the screen here because there's a bunch of other examples I want to get through. So one last time, I'll call run print my name. And we're going to say my name is Eric. It says, hello, Eric, right? And so run print my name every time that we call this function, it's going to give us a different value. I mean, you could make the argument that like if we give it Eric again, it gives us the same value, sure. But there's if we think about this from the perspective of like observing the function, there's no guarantee that when we call the function, it'll give us the same value because it's relying on what the user inputs. And like for example, I've got this is a good time. I've got an example of this later where it's expecting, for example, it's expecting an integer, and if you don't give it an integer, then it'll return an error. So that kind of shows the concept of that a little bit better. But what I'm going to get onto now is file reading. So you've seen this get line function. This lets us read from standard input. Let's say we wanted to read some file, right? And so first thing I'm going to do is I'm just going to try to read a file that doesn't exist. And you'll see what happens there. So we're going to say I want the contents of the function. I want the contents of the file, and I'm going to use this read file function with non-existent.txt. So this is just a text file that doesn't exist, and I'm going to try to read from it. So what's going to happen here? We talk about Haskell being pure and being perfect. There are still ways to have it throw an exception at runtime. Of course, it can. Any language can throw an exception at runtime. There's maybe a few that can't, but this here, like because we're explicitly telling it to read from this file, and we're not telling it to check if it exists, we get an exception. So if we were to run this in our code at some time, actually a good example of this would be to put it into our main function. So after we print the result, then we're going to read non-existent, right? And so you can think of this as like a program runtime, like we're running our application, right? We're giving it these values, And then all of a sudden, the program execution gets to this part of the file or to this part of the code that's expecting the file to be there. We get an exception, and the application crashes. Actually, a better way to show this would be putting it before we do this. So you can see that the application will actually crash, and we won't be able to see the result of 1, 2, 3, 4, right? So this line never executed because an exception was thrown, right? And so this is bad. This happens a lot in impure languages because there's no guarantee against it. It can also happen here because we're explicitly telling it to, but we wouldn't just do it like this. Like Haskell gives us the ability, and if we just look at read file, like we know just from the type signature that what did I do? Come on, I clicked on something by accident. My computer's slow today. Bear with me. You can see here that it's just IO string, right? But there's nothing here that tells us like what if the file doesn't exist? It's just IO string. It's basically this function assumes that it'll always exist. So this function on its own is not a good function to use. But I'm just showing you that here. So what if I wanted to do this in a safe manner? So I wanted to say, okay, read oh yeah, okay. So if I want to do this in a safe manner, I can use a function called try. And there are other functions. I'm just going to show you like how this works. So this safe read file function likely already exists somewhere. I'm just rewriting it. And all this is going to be is it's going to be the try function composed with the read file function. And this, sorry, I got that wrong. And so now rather than just being an file path IO, it's going to be, so I'll show you what the error is here. Oh, variable not in scope try. Oh, yeah, I've got to bring that in. So I could look up on Google where that function comes from, and you would notice that it comes from control.exception. And so now the error is saying could not match expected type. It's hard to read at the bottom there. Let me. Could not match either string with unit. So now you can see that because I've composed read file function with try using the dot here, we're now seeing that it's expecting to return an either error or string. So this is what we want. Like we always want either's. Realistically, either's or maybes. Like they're probably the two most important monads in Haskell. Like you can use IO. IO's great, but as you've seen, like IO on its own, it can still throw an exception. And so what we really want in a lot of these cases is an IO either of the error. In this case, it's going to be an IO error because IO has that defined, or a string, the string that we want, right? And so now this function is valid.
I think the name of it is actually IO exception.
IO error works too.
Oh, okay.
Yeah. Trust me, I'm writing off of code that I tested last
Fair
night.
enough, fair enough.
I'm not just winging this. So if we do this here, and I'm sure there's a difference between IO exception and IO error, but for the sake of this, it doesn't matter. And so now we're basically going to just do this, but in a safe manner. And so if I say, result, or we'll keep it contents so that it looks the same. And instead of read file, I'm going to use safe read file of non-existent.txt. So now if I look at the type of contents, or it won't tell me because I've got another error. Oh, it's just complaining that it's unused. But I can check the type of contents and it'll tell me that contents is of type either IO error string. I think I could use a type hole. I need to add a, don't worry about that, okay. So now, what I can do is, you've seen from the pattern matching lesson last week. Case, we're gonna use a case switch here to, or it's not result anymore, sorry, contents. And so we're pattern matching now on the either type. So either is a type with two possibilities. And so for the left case, left is always our error case. It's like left is literally just this left and right. So it's the one that's on the left or the one that's on the right. So in the case of left, we get an IO error. And so we're going to just print out the error. Yeah.
Just put in the chat as well for reference if you guys want to see further, like why does either look like this, or why can we pattern match on left and right in the context of either. The data declaration is the reason for that.
Yep. Otherwise, we're going to just print out the content that we have, right? And so we've got left, in the left case, we're going to just print error with the error. And in the right case, we're just going to print the content. We could just like return the content or something like that. But right now, you'll see an example of that later, but this is fine for now. So now this function is the same as this function, but it's handling the error, right? And this kind of just shows you why it's important to use safe functions. You can note like read file on its own is not a safe function. It's just kind of there because we need it. But if we use a safe function, it's going to enforce that we handle both cases, right? And so this is a little different than in traditional programming languages where you might use a safe function, but it's not going to enforce that you handle both cases, right? And so with pattern matching, if I forget this, it's going to tell me, and we can turn this warning into an error, but it says pattern matches are non-exhaustive, right? So we need to handle both cases. Now, if I, instead of read non-existent, I say read non-existent safe. And you remember when I called this before, we didn't see this result here. If I now call main 1, 2, 3, 4, it's going to print out the error. It's handling it, but then it's also continuing the program execution. So it's not actually crashing our application. This is being handled appropriately. So we can do whatever we want to do inside of this error case. Maybe we try again. Maybe we just log to the screen, like log to the log to let people know that like something unexpected happened. Maybe basically we're in control of what happens now, as opposed to it just randomly failing and crashing and then our customers getting upset. We can actually look at this case, we understand what happened, and we can deal with it. So what's next here? So I'm going to show an example of like isolating IO to the boundaries of the application and then using like a pure function to actually process the file contents. So all this is going to do is it's going to take a string and it's going to remove the lines from it and it's going to reverse it. So we'll use some functions that you may or may not have seen before, but that's okay. Map reverse over the lines content. So we are taking the content here. I'll show the lines function just so this makes a bit more sense. All right, so this just takes a list of characters terminated by \n. For those who don't know, \n is the way that we represent a new line in programming. So if we have a bunch of things on a new line, it's going to turn those into actual how do I say this? Like it'll turn it into an actual once you actually print it, it'll show it on a new line. But when you're actually looking at the string, it just has a \n in the string.
So multiple lines could be one string.
Yeah.
Yeah.
And so that's all this is saying. And then we're just mapping reverse over that. So it's going to take the lines of our code, map reverse. Basically all you need to understand is this is our, let's say this is our very complex program logic. This is what we want our program to do, right? What we want to do with our program, basically the majority of our the majority of our code should be functions like this. I would argue 90%, 95% of our code should be these types of functions where we're not relying on any kind of IO action. We're doing things in a pure manner. So if we want to process this file, say from a file path, we're going to say process file. And we're expecting an either IO string or IO error. Safe read file path. I actually don't think we need this. We'll put it back if it says we do.
You shouldn't because it's already annotated by the
Yeah,
safe
exactly,
read
exactly.
file.
Um,
And
so,
yeah.
go ahead. Sorry.
Well, the reason we would in case you're following what I'm saying there, the reason we would need to annotate in some cases is just because it's actually possible to using the try function to have multiple different types of exceptions.
Yeah.
And so it's really cool. Just based on the type that you specify, Haskell will look for that type of exception and ignore other kinds of exceptions. And so we're telling the compiler specifically to use the try that is going to look for an IO error.
Yep. And so, for example, there, if I believe if I take this away, let me start. Yeah, then we got an error here. Which is interesting, right? So here this is
Because
basically type inference at work, right?
you commented out the file or the
Yeah, I did
code
that on
base.
purpose.
Oh, okay.
Yeah, yeah. So what you're seeing here is that this function's fine. I mean, it gives us a warning because it wants every function to have a top level binding, which we should do. But you can see that it's kind of interesting how the type inferencing system in the Haskell compiler works. It is not as nearly as powerful. C# has type inferencing, but it's not nearly this powerful. If I remove this, you'll see I actually get an error up here on try because now we're saying ambiguous use of try. Whereas if I'm specifying later on in the program execution that this is an IO, either IO error string, it now actually fills in about it basically now try up here can infer based on its usage later in the program, which is extremely powerful. is kind of cool too. But if you're wondering why, like when I remove this, it throws an error up here, it's because of type inferencing. And so now the whole application is able to infer the type of try because we've specified here that when we use safe read file path, we want it to be either IO error string. But we will not do that right now because it's really just like niche nuanced cases where you want to do that. And it's really just to make writing the code cleaner sometimes. But in that case, I think it actually complicates the code. So we're just going to keep the type signature up here. Okay. So this function, all we're doing is we're going to read the file, and then we are going to where did I put the name of the file? Yeah, okay. We're going to read whatever's in the file and we're going to reverse it. So I'm just going to say safe process file test.txt. And so there we go. If I look at what's inside of test.txt, it says, hello, this is some data from a text that file that I wrote. And you can see here, oh, I turned it into a sad face. Hello, this is, if you can read it backwards, some data from a text file that I wrote, sad face.
Talk about some unintended side effects.
This was intended.
Yeah, yeah, fair, fair. I mean, if it's reversed, then
Like, watch, if
yeah. No, I fully joke. Like
I know.
the sad face, you know.
Yeah, yeah, I can't see. But if I do this, or you know what, I'll keep both just to show the new line part. Right, so it does both lines individually here. So that's why we use lines and unlines, is so that each line gets run through the reverse separately. It doesn't just like reverse the whole thing. But yeah, so there you go. You can see it backwards and then reversed again, right? And so this is our application logic that we're doing, but we're relying on the file to come through. And so if I try to run this on a file that doesn't exist, it'll tell us that it got an error. This is might seem insignificant because it's such a small application, but there's a huge benefit of isolating all errors to the boundary of your application. And that's that basically you want to minimize the amount of code that can fail, right?
I'll even add too, like you know, because you know, to illustrate the points as best we can, we're using like read file, right? Where like there's only one real. I mean, there's a couple ways that read file could fail, but the most common way is just like the file doesn't exist or whatever. In the context of ACE, I think a great example that like I've used, you know, this sort of logic for is using like OpenAI. So, for example, I wanted to build a system that just verified that names are appropriate, right? That no one has an inappropriate name, and the best way to use that was ChatGPT. Like I could, you know, use some other you know other more complex method, but like I figured the quickest way I'll do this is I'll use ChatGPT, and it did seem to work like quite well. However, every now and then ChatGPT will throw an error, right? Like maybe I've done too many requests. You know, maybe the data type that it gave me back. Like I'm instructing OpenAI to give me back either true or false. And sometimes it might give me back, yes, this was absolutely the perfect name or whatever, and I'm not expecting that. Um, and so, like, if that happens, then I need to fail in that case. And so, failing in that, explicitly failing in that case, means that I can isolate the failure to that and stop the failure from breaking the rest of the API, right? So like when you submit your onboarding form and you say like, I'm a front end engineer, my name is Galen, I'm looking to interview, et cetera, et cetera. There's the part that like we take that handler and we add in this ChatGPT logic to verify that your name is correct. We wouldn't want to have that entire onboarding form fail because it'd be like it's not your fault that ChatGPT broke or something. And so in that case that ChatGPT was to ever break, we would just accept the name for whatever it is. And so that's obviously not ideal. We don't want anything to ever fail. But what if it does fail? We have to as developers think through how we should handle that. And in the context of ChatGPT and using AI in general, I think the best way is just to say, okay, you know what, it failed. What's our backup plan?
Yeah,
Yeah.
cool. And so I switched over to my other. I don't know what was happening with the formatting, but now you can see it's not dark gray, so it's a lot easier to read. Um, so this function here is basically the same kind of concept. We are just using, oh, in that case, I do need it because I'm doing just inline here. Try doesn't know what type. Okay, so now what we're going to do is we're going to take one file and we're going to copy it from one destination to another destination. So really all we're doing here is we're reading a file and then writing a file. So what we need to do, and you'll notice here that I'm using these safe read files inside of the IO monad here. And so it's actually, I get the result, and then the result from read files or safe read file is that IO, or sorry, that either IO error string. And so we need to pattern match on the first one. So we get left error, put string. So if we get an error on the first one, we're saying there was an error reading the file. And then subsequently, if we get an error on the right result, we're saying error writing file. All of this is enforced because of the types that we're using. So we can't just like not put in an if or an else. We have to deal with these. And a lot of this too is like, you know, everyone has a little bit of ego about the code that they write. Um, I've never seen someone who doesn't. And you can always say like, oh well, I'll just make sure that if it returns a try that or if it returns an exception that I'll check for that exception. I'll make sure I wrap it in a try catch. I'll make sure that I use that I have an if and an else statement. Um, but the problem is that you're not the only person writing code. I mean, maybe you are, and in that case, like, feel free to write however you want. You are still kind of like, I'm sure you'll make a mistake at some point. Everyone does. But the important thing to note here is that like we're not the only people writing our code, and you're also protecting against yourself in the future, right? So you might write this function, um, and you know like right now I'm printing to the line, but for example, like if I just wanted to return the either error or like either string, we'll say, right? And so like we could write this function in a way that specifies to the user that it's going to copy a file and it's either going to give us an error or it's going to give us a success that the file was copied. And this is important because when someone comes to use this function in the future, you want them to be enforced to use it correctly. Like you want to enforce that people who are using your functions are using them correctly. You also want to make sure that they're not just adding some random logic into the middle. So yes, this is IO. You can do a lot of stuff with IO, but you can constrain this as much as you want to say like, no, I only want database actions to happen in this function, for example, or I only want writing to the file I don't want to read from a file in this function. Like you can do all of this. We're just showing you IO for now, but like this becomes in library developers use these and they create their own custom monads and types to enforce that like no, we're only gonna allow Postgres we're only going to allow valid Postgres calls inside of this function. And so like if you try to do something like you try to read a file inside of that function, it won't let you. Um, and that really protects against other people editing your file or other people editing your functions, yourself editing your function in a way that, sometimes we get lazy and we're like, oh, well, it would be easiest to put this random call to the database inside of this function that has 200 lines. That would be the easiest thing to do. But the problem is we're not always thinking about like what are the side effects of doing that. And so here we're able to constrain the side effects. Right now we're saying anything with side effects, but we are able to like, as we'll see in the future, with like when we get into monad transformers and like other types of monads, like you're able to build on top of IO and constrain it further, right? So we want only IO actions that interact with the database. And in order for it to interact with the database, it must use this type system. And so now we're saying like, okay, it has to be, you have to use a select, um, or you have to use, like for Postgres, like for doing likeness in Postgres, like I like is the syntax in Postgres, but I believe it's different in MySQL, right? And so if we want to make sure that no errors happen at runtime, because for example, if we were to do a syntax error inside of an SQL query, that would be a runtime failure because SQL is uh, outside of our program's execution. And so we don't know if the query that we send to SQL is going to be valid until we send it there and get a response back. So oftentimes, like you'll see, we've used Postgres in the past. We're using the actual Postgres types, right? And so someone has written a library that enforces that we use those types rather than putting in a string. And so that's just a kind of an example of like why this IO stuff matters. It's like, yeah, right here we have IO, that's fine. But like we can do way more than just IO. Like we can have like 6 layers on top of this IO that constrain it into exactly what we want it to do. And we'll get into that more. That's more of something that you need if you want to write your own library. But understanding it can help you see why like why the language is so powerful. Um, and it's really just about safety, like protecting against errors being introduced in the future. Anyone who's worked in the software engineering industry will know how important that is. I find it's like before I actually got a job as a software engineer, I kind of overlooked the importance of this, right? Like I was kind of like, well, I'm just writing like because you don't see it as much when you're writing your own code. And when you're writing your own code, like you're kind of used to this idea of debugging. So like you run the code and then like you make a change and oh, it broke. I'm just gonna fix it, right? But if you think about like when an application's actually in production, when people are using your application, like let's say there's 100,000 people using this application, like we can't just we can't just like run it and then find out if it breaks, right? Like we need to know if it breaks before it actually ships to the user. We could write a bunch of unit tests and everything, but it's much easier. And even in writing unit tests, oftentimes you're just reinforcing your same assumptions. Like the person who writes the code should never be the person who writes the unit test, but that's never how it works. Like it's too inefficient to get someone else to write unit tests for your code. So you'll never see that happen. Maybe you will see that happen, but I've never seen that in the industry. And that just comes down to like cost. So like there's all these different variables that you're battling against when you're actually a software engineer at a company. Like when companies are paying you to write software, um, they really value efficiency. And so to be able to enforce that nothing will break at runtime while you're writing the code is extremely valuable to companies. So for this one, just because we're getting up to 11:30, I'll have like 2 or 3 more examples to show. I'm just going to kind of pick up the pace here a little bit. We're going to say I want to copy a file from copy this .txt to copy this copy .txt. And so now we successfully copied the file because copy this existed. If I say copy this to error reading file, so it didn't find the file. But if I look, copy this has this text, this data is copied. If I go to copy this copy, we also have that function. So it read in the data and it wrote it to another function. Very simple function. But you can see here how we can kind of chain these together to deal with the, and then also be enforced to deal with the left and right case in both cases. Okay, last couple of examples here. I've got a function that gets a number. So this is a pure function. Just gonna really just show you the difference between pure and impure. Like this is probably the easiest way to, I mean, you would never really write it like this, but this is showing you. So basically, it's kind of confusing using pure here. So the return function is how we return from the IO monad or from any monad. Return.
I should add, if you're going to use return in this context like that, yeah. So you can see the type there that it's like A to IOA, or for return IO. Ultimately, return just means like wrap this. So
Yeah.
like in the context of IO, wrap this in IO. Wrap this in an
Okay.
IO label
Yeah.
and modifier. So yeah.
So this is like you would, it might seem a little nuanced right now, but basically this, even though this will always return us 42, we are essentially, it's not lifting, but it's wrapping. I guess it's the opposite of a lift technically, right, Galen?
Um,
Because a lift, to my understanding, would take the 42 out of the monad.
I guess like I don't use that language too much. But like
Yeah.
I like unbind. If lift means the same as unbind, then sure, yeah.
Yeah. Yeah. So that this is a quick little example of like the difference between integer and IO integer. At its simplest core, like we're basically just saying, okay, treat this as an IO monad, but we're not actually doing anything. And so this, like for example, I could do like, right, and then put strline val, and then return 42, right? So like this is how we would represent a pure value in an impure context. It's still always going to give us that same value, but we could,
You could return the val too.
I could if it was a string. So I'll just make, just for sake of how this works, IO string. I could either return string 42 or I could return val, right? And so both of these are exactly the same. But just to kind of show you that like what return does is it actually just takes a pure value and returns it to the monad.
Almost like an upgrade, I
Yeah,
guess.
it upgrades it. Yeah, it's a good way of saying it. So to kind of go on to this one here, we've got get number from input. And so this is going to give us either a string, which is our error, or the integer that we put in. So we'll say get number from input equals do. I'm just going to copy this code for sake of time. So, and read maybe comes from this package here, text.read. And like the easiest way to find that is to just go on Google, right? Look for, okay, read maybe, where does that come from? It comes from text.read. So then we just import it. So yeah, so here what we're doing is we're using read maybe. Read maybe is a safe read because it gives us either a maybe, or it gives us either just the name or nothing. And so what we're doing here, and this is actually using type inference. So you'll notice that like there's no value of read. So you can see here we're using a polymorphic type. I think this is actually important to discuss. So you can see here read maybe. It's using a type class constraint of read. So any value that can be readable is what it'll read. So if you remember from previous lessons, lowercase letters in the type class mean that A is polymorphic. A can be any value, right? If we didn't have this, oh shit, sorry. If we didn't have this part before it, A could be literally any value. But what we're doing is we're constraining A. So we're saying, okay, A can be anything as long as A implements the read type class. And so if you look at read, if I go into source here, where are the instances for read?
Oh, if you
If you know off by heart.
well, if you just go back, you just didn't scroll far
So,
enough.
oh, okay.
It's showing all the. It just has a long explanation.
Oh yeah,
And
right
then
here,
you
right
see
here,
the
right here. Yeah,
instances.
yeah. So these are all of the predefined instances for read. And you can see here that if we keep scrolling, read int and read integer. So the function that we have has an implementation of integer for read. So that means we can read into an integer. And the type inferencing knows that because we're returning an integer, in this case, just n, write n, right? Because we're returning an integer here, that this must be an integer. Like the results of read maybe input must be an integer because we're returning an integer. You know, if I were to put string here, then this would return a string as well. So it's using type inference in this case. You could do something like this. Where's that going?
What are you looking to do?
Specify the type. Yeah, like you can see here how it's saying read maybe 123 maybe int. So you can, and then for example here, if we're saying read maybe hello maybe int, no, I'll actually just do this in the
So I guess if it's not of the
REPL.
type that we are expecting, it will just give us the nothing case.
Exactly. And that's because I gotta load data.
Or or text.read. You just say import text.read or
Oh yeah, it's just import, right?
yeah, you literally yeah.
Yeah, okay. Right, and so read maybe, if I did hello here though, without specifying that it needs to be an int. Wait, what?
Well, well, you haven't specified anything, so
Oh yeah, so it's
if
just not even, yeah. There's no type inferencing happening here, which is why that happens. The heck?
um,
All right, well, I'm going off track a little bit here. I'm clearly doing something wrong. Does,
oh, I think if you did this might just be a peculiarity of. I mean, it's not often that you would even do read maybe of a string because that like doesn't make any sense. But
yeah,
if you have like that string wrapped in quotes, that might work. Like if you do backslash on the like let me just type it out like this.
like this?
Like what I did in the chat.
I see what you're saying, yeah.
Oh, you gotta specify.
Yeah,
Yeah.
that was what it was. So that's just a peculiarity of the terminal.
Right. And
So the terminal was escaping, it was basically getting rid of these outer quotes. So we just needed to say this is the actual string that gets read. So when you work with terminals, you'll kind of understand how that why that happened.
also
But
also well more specifically I think it's actually partially by design. I like if you there's a like in Haskell a lot of like Haskellers like to use like, the concept of laws, so you'll see like this function always follows this rule. So I think the law here is that for anything that you would let's say like any input you would call show and then read on, that it would return that thing.
yeah,
So for the reason I knew it was the extra quotes for hello here is because if you do show of a string, it will add, it will escape the string. Um,
right, right, yeah,
but that's getting off track for sure.
yeah.
The key point is
But
just
the
maybe
the
int.
yeah, the key point here is that this we're being explicit about the type, and here we're being implicit about the type. So this is kind of nice because like if we had to write this everywhere in the code, it would just get really messy. And so because it's able to infer the type from this integer being here, we don't need to specify the type. So read maybe knows that this needs to return an integer. Okay. So if I reload data.text. Okay, I'm doing something wrong. Quit. There. So get number from input, and we're going to enter an integer, 42. And it gives us right 42, which means there was a value. If I enter hello, left error, invalid input, not an integer, right? So we can see how read maybe gives us the ability to read a value and then constrain it on a type. So we want input to be an integer. Okay, there's one last function here, and this is actually the base template for the um, very first project. Is that you'll be asked to create a command line application. And so a command line application is basically just, I mean, it's kind of like what like GHCI is a command line application. So like we give it a command, it gives us a response. that we're asking you to build a to-do list with this like this style here. So we're going to say here, enter command. We're going to flush the standard output. This is just this is a byproduct of C because of the way that we're not going to get into why that is needed. Just know that you always need to flush your standard output buffer. And it's basically just because of the way that CPUs work. They're 32 bits at a time. So if what you read is not 32 bits, sometimes, or 32 or 64, I guess now, 64 or 32 bit. If what you read does not take up the entire thing, sometimes there'll be fragments left behind. And so like you can print part of the previous response. That's an interesting lesson in itself to kind of get into that, but we don't need to. That's something that you really have to deal with when you're working with low-level languages like C. But here we do need to flush the standard output. So basically, I'm just writing the code here, but this is now mixing recursion with the idea of I/O. I need to get hflush from system.io. Okay. And so basically what we're doing here is we're saying, okay, I'm going to create a function called loop. All loop is going to do is it's first going to put a string asking us to enter a command. It's going to flush the output. It's going to read a new line in. So this will be our input. So the command that we want to write. We'll just make that easier. Here, command. And so then what we're doing is we're going to have handle input be an IO action, but it's going to return us whether or not we should continue looping. So I'll show you what that, like why we do that in a second here. But if we're still looping, then we're just going to call loop again. And otherwise, we're going to just return the unit that that this IO function is expecting. Right. So this is going to loop using recursion. Okay. And I'll write this handle input function now, which just takes IO bool, handle input. So we're going to just use some simple pattern matching here. We could write a case statement, but in this case, it's, I think, easier to just kind of pattern match directly on the string. So we're saying if handle input is exit, then we want to do this. We want to put string to the line or to the console. We're going to say goodbye, and then we're going to return false. So remember, this bool represents whether or not we're exiting or not. Or I guess I should probably change the wording on this.
Should loop.
Yeah, should loop works too, but I'm going to just call it is exit. If not, if I'll just for sake of this here, just so it makes a bit more sense. And then this would return true. So here we're saying put stir line, and this is where we would actually handle the input. So this is where you would actually start writing the code for, you know, breaking these commands down. You know, maybe you even just do that with pattern matching. Like maybe you say like handle input add, right? And then you get into like another loop that says like, okay, what do you want to add to the to-do list? This kind of concept, right? But right now, all we're gonna do is, and that there, like pretty much hint, hint, that's how you would maybe solve this first project. So here we are going to just return false. So we're not exiting yet. So we're just going to print out the input that you write there. So reload this. We're going to call loop, and then it's just going to tell us to enter a command. So we'll say, like, for example, in the to-do list, we're going to add to the to-do list. It says you entered add. List. Maybe we want to list, right? And so this is just handling these different cases, and within here we can pattern match more on the input, but primarily you'll see how how this pattern matching works is if I type if I type exit, it says goodbye and it exits the loop. Now, just as a quick demonstration of how pattern matching works, what if I were to do it in the way? Well, luckily enough, the compiler can actually tell us that this pattern match is redundant, but just to kind of showcase what happens, and that's a warning, whatever. If I say loop and then I type exit, it's going to say you've entered exit, right? And so pattern matching occurs from top to bottom. And so you always want to have the more specific cases be first. Input is literally catching everything, so it doesn't ever actually get here, even though that we've typed in exit. That might be something that you may or may not run into, but yeah, that's what kind of makes this so good for recursion. These pattern matches is because we can always define the exit case first, and then we can get into all the different logic cases, right? Like if you had add here, right? You would want, I mean, I guess in theory you could have exit be before, you could even have exit be after add because these are both specific, but you may or may not run into a case where like you're like, why is my pattern not being matched? Check the order of the patterns.
Well, I guess it's like a Venn diagram, right? Like, I mean, like sometimes like a Venn diagram, there's like no crossover, no intersection.
Yeah.
Which in the case of exit and add, there's no intersection. But in the case of input and exit, input, fully maps around the example of exit.
Yeah. Yeah. And the compiler will tell you, but yeah, there we go. So that's IO in a nutshell. We could go more into it. I don't think we need to, but just one final thing to understand is that any time that you have a side effect, and I alluded to this earlier, but anytime you have a side effect in your code, it's always going to have IO somewhere in the uh, code. So if I look at data declaration for snap, or no, that's the
And what
monad.
is snap?
So snap it's a library for doing requests, so doing HTTP requests. And so you can see here that even though we're doing, we're basically putting everything behind this snap A action. Snap A actually takes in all of this information, and we're not going to get into this in this lesson, but the one thing I wanted to just show you is that it'll always end with an IO. So at every level, like, you might get these really complex types, but all they're really doing is just further constraining an IO action. They're adding more logic onto the IO action.
And
So IO is the primitive value
yeah,
in this case.
and you'll see that any Haskell program, you'll find a main of the type IO unit.
Yeah. Yep. Which also means that request and response need to be handled before it
Yeah,
exits,
totally.
because you can't return an IO request response from main. So like you always need to come down to IO unit, meaning everything has to, like, all these values need to be dealt with. So it actually enforces that at the type level, which is nice. But yeah, we've got 4 minutes left. Kind of went almost right to time. We do have, like, we can go over by about 10 minutes if anyone has questions. So feel free to ask, or if everything that we said today made sense, then we look forward to seeing your project submissions. Because this is everything you need to, like, at this point you should be able to complete project 1 and 2 based on what we've discussed so far.
Mhm. Yeah. Are there any questions?